All right, how's it going, everybody? Uh, I am recording this video here on Thursday, January 14th. We're getting our start to the spring semester here. Um, Doing our first, my first Calc 2 video of the semester. You guys will have already seen, I'm sure, my video from associated with Chapter 5, Sections 1, 2, and 3. I'm reusing that one from the past semester, but I will be making new ones for this semester. I'm intending for a vast majority of things this semester, if not all the videos. So we will get some fresh new things here this semester. So really where this class is supposed to start is with section 4 and chapter 5 here, indefinite integrals and the net change theorem. I'm definitely aware of the fact that not everybody's Calculus 1 class ends at the exact same location, and that's why it is a little bit of your responsibility to make sure that you have covered all the material up until where this class officially begins at section 5.4. That's why I've made sort of the algebra trig and calc 1 refresher content for you guys. That's why I've made the section covering sections 1 or video covering sections 1, 2, and 3 in case you do need any of that content there. And I will say also before we get started right here, I did put it in our weekly guide, but it is certainly the case that this week 1, is the most number of online homework questions that you will have for the entire semester. And the reason that that's really important is because this class is hard, because it matters that you are fully competent, and I mean fully competent in your algebra, your trigonometry, your calculus 1, your ability to think in terms of Riemann sums and do basic integration, since we're kind of starting with some not really advanced integration, but not the easiest stuff either right away here today. And so it matters that you are prepared for this, because this is just a hard enough class that you can't really do this softly. And I don't want to be scary by saying this is hard, but it's certainly not going to be super easy. So it matters that we do some real work in the first week and make absolutely sure that we are have the skills that we need to do the rest of the content that's associated with this course here. So I'm going to get started here with some 5.4 things so I don't drag this out too unnecessarily long here. And in general, what I'm going to also say is the expectation is always going to be that you have read the book, taken some notes, worked through the examples that are in the textbook before you watch these videos. And so occasionally at the beginning of the videos, rather than me discussing the concepts from the textbook here, me saying, I know that you've already read the textbook. Here are some highlights of the things that I think were the most important things in the textbook. And then we're going to work through some examples together, because I want you guys to have I think a lot of what's going to happen in this class this semester is that the doing is not too bad, but the thinking and the building your own components is the stuff that can be a little bit trickier. I think what we're going to see here today is that as long as you're comfortable with your content in 5.3, then the integration that we're going to actually do today is going to be pretty easy, but building the integrals that we want, that's going to be the hard part. And that's why I think it's really meaningful for you guys to watch me work through some examples here. So, Section 5.4, indefinite integrals and the net change theorem. So when you read through this section, I do think this section presents itself pretty straightforward. We're going to see some sections later this semester that are going to be a little bit less straightforward. I will need to spend a little bit more time on more direct concept related things. But I think that you guys are going to read this and you're going to say, oh, okay, yeah, I got that. But I do want to point out some of the things that are important in here. First things first, on page 406, there's a table of indefinite integrals. This is literally the reverse of a table that the book has previously used in a derivative section back in chapter 3 somewhere, because we know that derivatives and integrals are almost perfect inverses of each other. They've got that little difference of the plus c, but they're almost perfect inverses of each other. It's good for us to think of integration and derivation to be inverse operations. And so this table is really just a flipped table of a derivative table that you've previously seen. So this is sort of saying, remember that you need to know how to do derivatives backwards, because that's really what we're doing when we're performing integration. There's another important example that even if you've already read the section, it's worth it to go see what exactly is the highlight of this example. Example 5 in the textbook that's on page 407 is a great example of where sometimes people get a little overly excited about performing integration. One of the themes that we will see this semester is that integration in general is hard. And so you always want to be integrating the simplest expression that you possibly can be. And example 5 on page 407 is a great example of where if you attempt to just take the integral of some expression right away, you won't be able to. But if you stop, do some algebraic simplification, it turns the expression into something that will be much, much easier to integrate. And so this is just the first of many times that I'm going to point out this semester. Remember to do as much algebra as you can before you do the calculus steps, because we want the calculus steps to be easy, because integration can get to be impossible, really, in a lot of cases. There's a ton of things that just are not integrable, and we want to work to create expressions that are meaningful and integrable. Finally, on page 408, the book defines the net change theorem, which is clearly sort of the namesake of this section right here. The net change theorem isn't anything too crazy. It's really just sort of an alternate formation of the fundamental theorem of calculus, saying that a definite integral, we're going to find the indefinite integral, and we're going to apply the upper bound to the indefinite integral's value and subtract off the lower bound being applied to the indefinite integral's value. But the meaningful part about the net change theorem is that it's sort of expressed in terms of a significant number of applications that it's saying why do we care to compute definite integrals. The book gives 8 examples. There's sort of like a bulleted list with 8 items. They're really good, and you really need to read all 8 of them. The reason that we like this textbook so much is because it does do a pretty good job kind of bringing your math knowledge and what's being taught as the math knowledge in the book to your real world experience, so that you can stop and say, oh yeah, that is how that thing works right there. So they list 8 really clear examples, in my opinion. And importantly, the final 3 examples that are listed right there deal with distance, displacement, and the relationship between position, velocity, and acceleration. Those are the last 3 of the 8 bulleted examples right there. We're going to work through examples that are related to those 3 ideas in our video here today. So we'll see some examples that are directly related to those. So here's just some of the highlights that you guys should have seen in section 5.4. Go back and double check that you really did take away the meaningful thing that you were supposed to there. And again, 406, that's really just a reference for you for that table of indefinite integrals. Example 5, just make sure that you see that the algebra is meaningful there, and it had to happen first before the integration. And the net change theorem, it's just, like I said a second ago, there's going to be many situations this semester where performing the integration isn't too bad, but knowing why we built the integral the way that we did, that's kind of the more difficult part of the process. And so I think reading through those 8 examples about the net change theorem kind of help reinforce the why did you build that integral that way. They do a good job kind of following some units around and giving meaningful examples as to why that integral expression represents the desired real world quantity that we're interested in describing. So let's kind of get right into this and do some examples here. Basically, today what I'm going to do is I've picked out some problems from the textbook that I think are exactly what I care for you guys to be able to do. In later sections, we will either go into more detail about the examples that are in the book section, or I'll make up my own problems. But for today, the numbers that you see, like the 43 right there, that's a reference to like one of the homework problems at the end of section 5.4. But again, I'll vary as to kind of how I approach sort of my selection of examples and stuff like that. Let's take a look here. So our first example of the semester, I'm so excited. Find the area in the first quadrant bounded by the curve x equals 2y minus y squared. I want to point out right away, the first reason why this is going to be my first official example of this semester is because I didn't want to do anything too easy. And this one's already a little bit weird in the fact that we have describe this as an x in terms of y rather than y in terms of x right here. So one of the things we're going to have to stop and think about here is how do we reorient ourselves to think in terms of sort of swapping the role of x and y. So in general, anytime that I know that I'm looking for some sort of geometric property, like simply an area, right? This isn't really like an application problem. This is purely a math problem here. Find the area. We know that integration will help us find area underneath the curve. So I know I'm going to want to set up an integral, but what I really want to know before I get started here is what does this shape even look like here, right? So find the area in the first quadrant bounded by this curve. Well, one thing I can do real quick for myself is I can tell that I can factor this. And getting into a factored form there, since we're quadratic in y, does help me see things like, I do know that it looks like here I'm going to have, if y is 0, then x is 0. That's obviously an intercept on our graph. And I can also see if y is 2, then x is 0. So I know I'm going to get this second point on my graph right there. So I know that at 0 and 2, we have y-intercepts rather than x-intercepts since we've swapped the roles of our variables. I do know that this is going to look like a parabola, but since I'm not used to thinking about things where it's x being described in terms of y rather than y being described in terms of x, I'm not quite sure how to think about whether or not this parabola opens to the left or to the right. So what I'm going to do is I'm going to stop for 1 second here and rewrite this in the way that I feel like I normally see it, which is 2x minus x squared. In this case here, I know that this would be, let's see, 2 minus x. So I'm going to get roots at 0 and at 2. And what I know is that because there's a negative on this x squared, this guy is opening down, right? So I know that that's my super quick sketch of what this would look like if I were to flip my variables back to being in terms of y in terms of x. Right? So all I want to do now is rephrase this in terms of my original graph. I can see that this parabola opens down. It opens along the negative y-axis. Therefore, this one should open along the negative x-axis over here. So this is sort of my analogy drawing over here. So I know that our actual parabola of interest is going to be doing something like this right here. So what I know is that my area of interest is really this piece right here. I'm interested in finding this area. It's in the first quadrant. It's bounded by the curve, right? So I'm thinking to myself here, maybe I can give myself a little, like kind of shade this in. This is our region of interest right here. Color this guy green. This is what we're trying to find. Here's our area that we want. All right, so what we got to think to ourselves is how are we gonna find this area? And what I want to really strongly encourage here, and I'm going to do a lot of this in the next couple of weeks, is we should always be thinking in terms of our Riemann sums, right? So our shape of interest kind of looks like this guy right here, right? There's our parabola and our points that are located here at 0, 0 and at 0, 2. Those are our 2 points right there. What I'm thinking to myself here is that I know that my area is going to be found by performing some form of integration, right? The sum integral is going to give me the area that's underneath this curve. What I've learned from my Riemann sum experience in sections 5.1 and 5.2 is that I want to think of integrals in terms of the Riemann sums from which they came. What that means to me is that there should be some rectangles that I'm imagining in this diagram here that I want to add up an infinite number of to accumulate the area of interest. So what I know is that if we are interested in rectangles, there should be some form of like a length times a width thing here, right? I'm adding up length times width. Do remember that this integral symbol looks like an S specifically because it's referencing a sum. It's S for sum. We're adding up a bunch of rectangles that all have length and all have width. What we need to decide for ourselves is, what do those rectangles look like? How do we describe that length and that width here? So what I'm picturing for myself is that when I'm talking length and width, well, that really just means to me X stuff and Y stuff, right? That's my width is my X values, my length, I suppose, maybe my y values right there. So I'm going to rephrase this as just saying, I want to multiply some x components by some y components, and that'll give me the area of a rectangle. Adding up an infinite number of these infinitely thin rectangles is going to give me the total area represented in our region of interest here. Well, what do I have? Do I have any way to describe my x stuff here? Well, I do know what my x values are always going to be. X right here. X is 2y minus y squared. All right. This is going to be my x component. So what I'm picturing for myself here, very importantly, is this is my Riemann rectangle right here. I'm picturing a whole bunch of rectangles that look like this guy. I'm going to draw this rectangle a little bit bigger here. This rectangle that I'm imagining right here has width of x, or we know x is 2y minus y squared. This thing, notice that we are imagining this Riemann rectangle. Now, very importantly, our Riemann sums, we know that every rectangle has that width, or we typically picture our vertical rectangles in our Riemann sums, that width of delta x. Well, here we've got a Riemann rectangle that I'm laying on its side. It looks like I've got a delta y, or a dy as our thickness right here, right? That's our infinitely thin. I'm writing it as a delta y. Infinitely thin should be our dy term, which is what we're going to use in our expression down here now. But I now know that every one of my rectangles has a width of x, where x is the same thing as 2y minus y squared. Every one of the infinite rectangles has a height of the infinitely thin dy, so that's my y stuff that I've got right here. Now that I know that I'm doing an integral in terms of dy, this now says to me I want to accumulate one of those rectangles for every single y value in the span of consideration. What we have sort of determined here, but this kind of came from our algebraic factoring, I know that the y values of interest span from 0 to 2, so it looks like those are the appropriate bounds of integration that are going to go on my integral here. So, as I kind of said a minute ago, I really think that the difficult part of today is not performing the integration, but building the integrals, knowing how to draw the pictures, thinking in terms of Riemann objects. We are accumulating an infinite number of Riemann sticks so that we can get sort of a Riemann sheet, right? Each Riemann stick, remember, really only has one dimension here. This is an infinitely thin dimension. They're sort of one-dimensional sticks. Adding up an infinite number of adjacent one-dimensional sticks is giving us a two-dimensional sheet that we're getting right here, the green sheet that we can see over here. So let's go ahead and perform the integration now that we've set up our integral. So just to kind of rewrite this without my parentheses here, it looks like this is just 2y minus y squared dy. So integrating 2y, I know I'm going to increase the power by 1, so y to the 1 becomes y to the 2. I know that if I were to take the derivative of y to the 2, I would get 2y. And that's exactly what I want. So it looks like we're good right here. The derivative of y squared is 2y. So working backwards, I'm good. I checked that and we're good. For the second term here, I'll give my minus sign. I currently have y to the second power. I know that integration adds 1 to the power whenever we're looking at polynomial terms. So I do know I'm getting something like y cubed. However, I know that if I were to take the derivative of y cubed, I would get 3y squared. I only want 1y squared, so I'm only going to keep 1/3 of that, right? Now, if I were to take the derivative, the 1/3 and the 3 will cancel, leaving us with just the y squared that we originally had. We still need to evaluate this integral now. We're looking at a definite integral, so we want to evaluate this integral from y equals 0 to y equals 2. One thing I want to point out real quick is that I know that if you're looking in the book, it certainly is not indicating our bounds exactly the way that I've notated them. I'm pretty sure it just says 0 and 2. I'm going to shake my fist at you guys many, many times in these first few weeks to say, you had better keep track of what variable we are evaluating over. What we're going to see immediately in our very next video, section 5.5, we're going to be creating new variables, and it's going to be very easy for you to forget which variable these values are referencing. These are y values. The y span is going from y equals 0 to y equals 2. In this case, we're not really at risk of variable confusion, but I'm going to set a good precedent right here and practice my good integration behavior, and I'm going to always remember what is the variable that we are describing when we say 0 and 2 for those bounds right there. And so here we can evaluate our antiderivative at the upper bound minus evaluating the antiderivative at the lower bound, and that will give us the overall result of our definite integral. And maybe I'm going to just kind of write some extra stuff for right now, just to make sure that we are all kind of on the same page. The book's notation for this would be to say that the function f of y is 2y minus y squared. I don't like the fact that this is the notation that's used, but I know that you guys have all seen it, that the book refers to the antiderivative of lowercase f as capital F. And this is our y squared minus 1/3 y cubed. And that the integral then from a to b of lowercase f of y dy is going to be, I'll write it right here, capital F at the upper bound b minus capital F at the lower bound a right there. So we're at this step right here. We've found our capital F expression. We just need to evaluate it once at the upper bound of 2, then subtract off evaluating at the lower bound of 0. One thing you should identify right away that's a very nice convenience for us here. Anytime we're doing integration with polynomials and 0 is one of the bounds, it's a guarantee that that entire term is going to go to 0. Notice that when we plug in 0 into this expression, we just get out 0, which is pretty nice and easy for us here. So I am going to write this out a little bit long form here since this is our first example here. All right, so here's our antiderivative at 2 minus our antiderivative at 0. It looks like what we're getting here is, what do I get? 4 minus 8 thirds minus 0 over here. 4 minus 8 thirds, I can write this as 12 thirds minus 8 thirds. Looks like I'm getting 4 thirds for our total area bounded in the first quadrant by this sideways parabola that we've got sitting right here, right? So again, I think that the most important thing that I wrote for this entire problem is really just my first like 3 lines here. How do I think about how to construct the integral? Thinking in terms of Riemann objects is going to be a really, really big theme for our first 3-4 weeks of this class. Thinking of how do I construct an integral that's going to give me some desired quantity here. Thinking in terms of our Riemann blocks associated with our Riemann sums is a super helpful thing to do. And we're going to see it again in our next example. In fact, in our next example, we'll do this both ways. We'll do this once with horizontal Riemann sticks and once with vertical Riemann sticks. And real quick, I guess before I walk away from that, since this is some verbiage that I use very commonly here, I feel like I take the Riemann verbalization further than I have heard other people do. The book will refer to Riemann sums. I refer to lots and lots of different kinds of ideas related to Riemann objects. In my mind, what a Riemann object is, it is an object that is one dimension lower than the object that you're trying to build. We wanted to find a two-dimensional area. And so the way that we did that is we constructed an infinite number of one-dimensional Riemann sticks in this case. What you're going to see us go do in the next chapter is we can do a similar idea. This was taking one-dimensional objects, adding together an infinite number of them to get a two-dimensional object. Next chapter, we're going to take some two-dimensional sheets, right? Like a sheet of paper, basically. And if you add up an infinite number of two-dimensional sheets, well, what you form then is a three-dimensional solid, right? So the way that we compute volumes is by integrating two-dimensional areas. The way that we get two-dimensional areas is by integrating one-dimensional sticks, like this guy right here, right? So I will very often refer to Riemann objects. The other thing that's going to change is that we're not always going to be looking at Riemann sticks. So I'm referring to this as a Riemann stick to indicate it's a rectangle, but later we're going to see that we're going to have Riemann circles and Riemann squares and different things like that. A Riemann object is an object that is one dimension lower than the object that we're trying to construct in this case here. Right? So this is, I call this a Riemann stick. It's got one dimension, just its width in this case, because we can see that its height was infinitely thin right there. That's the dy. That's an infinitely thin height, a one-dimensional stick. So let's go ahead and do this again, and we'll see kind of a both perspectives look at this next guy here. Let's go ahead and find the area of the region. It's bounded by, and here I just am using a little bit of bracketing to help kind of parse this sentence for us right here. It's bounded by the y-axis, that's one of its boundaries. It's bounded by the line y equals 1, that's a second boundary. And it's bounded by the curve y equals the fourth root of x. That's going to be its third bounding edge right there, right? And I'm going to suggest we should do this two different ways. Let's do this once with a dx integral and once with a dy integral. So in one setting, we're going to want to build horizontal Riemann sticks and add them vertically. In another setting, we're going to build vertical Riemann sticks and we're going to add them horizontally here. We'd like to see that we can build them both ways. We'd like to get the same answer, obviously, for both, since they're both representing the same area here. But this is, I think, a great example in learning to build the desired thing rather than just performing integration, right? So as with the previous one, the picture matters here, right? So let's kind of get our diagram of what's going on. I am interested in, let's see here. I'm going to draw one general picture. So I know that I'm bounded. So I know that this curve, by the way, only exists in the first quadrant. So I know I'm good to just draw my picture there. I know that one of my boundaries is the y-axis. So that'll be one of my boundaries here. The line y equals 1 is a boundary. So I'm going to give that as a dashed line right there. There's y equals 1. And the other thing we've got is the fourth root of x. I don't know, fourth root, a little bit weird, but I basically know that all of my even roots all sort of look like square root. The fourth root, so the square root is going to be, it's got our concave down shape. The fourth root of x is just going to be even more bent down right there, where things are going to get, okay, values larger than 1 are going to get even smaller. values bigger than 1 are actually going to get a little bit bigger out there. One thing that I know is that if I'm interested in a boundary point here, I can see that the points 1, 1 certainly agrees with this fourth root of x. So it seems like that's where we'll hit our bounding line of y equals 1 out there. So I do think that'll be sort of like a corner on our graph. That's our x equals 1 right there. And this is our y equals 1. So I'm picturing some shape that's doing something like this. Right? There's my fourth root of x. I guess I'll keep drawing it out there. But we are interested in, maybe again, I can get my green out. Here is our region of interest. It's bounded by the y-axis. It's bounded by the line y equals 1. And it's bounded by our the curve with the function that was given to us here. I need a Microsoft Paint paint bucket here to fill this shape in. All right. So there's our region of interest. So again, we want to do this 2 different ways. So let's go ahead and set ourselves up with two different formattings here. So one thing I would like to do is do this with a dx integral. A dx integral meaning we're going to accumulate rectangles from left to right. It's the x values that we're going to see. Every single one of the x values is going to get its own Riemann stick. So our dx setting is going to be over here on the left, and our dy setting will be over here on the right. And our dx setting, again, our rectangles are always going to be, I'm going to have to draw a new picture here for myself. All right, not a super great curve right there, that's okay. And in this setting right here, I'm going to want to build Riemann rectangles where there is one rectangle for every single one of the x values in consideration here. I should put my end point right there. That'll matter that we know that that's at 1 and that this is at y equals 1 right here. So here's my Riemann rectangle here. I want the infinitely thin part to be the x part. That's what dx is saying to me. Remember that the dx is the infinitely thin delta x there. On the other hand, over here, I can draw my picture at least right now for the dy one. We'll stop and actually do these one at a time in a second. I just want to get my comparisons out here. In this case right here, I want the infinitely thin part of my rectangle to be the y component. So in this case, I'm picturing for myself Riemann rectangles that extend horizontally, where we are accumulating one rectangle for every y value, rather than in the dx picture, we're accumulating one rectangle for every x value here. So what we now need to think about is, again, we're still thinking area. We're still thinking area is accumulated by lots of lengths times widths. We're thinking in terms of these rectangles. I know that length times width is really like my x stuff times my y stuff. But notice what we're going to represent the x stuff and the y stuff by is going to change, because in one setting I want my x stuff to be infinitely small, and the other setting I want the y stuff to be the stuff that's infinitely small here. So I'm still thinking to myself that my area is going to be my integral. I'm going to say my dumb version of this first, my x stuff times my y stuff. But here what I can see is that my x stuff is already sort of claimed, right? My rectangle here, my Riemann rectangle of interest, has this delta x for its width, or dx in our infinitely thin rectangle case, and it has just y, whatever y is, as its vertical component here. Well, I know what y is. It's the fourth root of x, or also known as x to the 1/4, right? So we can say here y equals x to the 1/4. That's what y actually is there, right? So what's my x stuff in this case? Well, it's dx. That's what the x component of each individual rectangle is. What's my y stuff in this case? Well, y is x to the 1/4. This is my y component. What is the height of each point on a rectangle? X to the 1/4, and that just depends on which x value you're looking at. Finally, I can see that I am doing a dx integral. I know that I want one of these for all of the x values of interest. Since our curve intersected the boundary of y equals 1 at x equals 1, I can see here that from 0 to 1 is the x bounds of interest right here. So this 0 to 1, those are x values. And finally, recognize that although we sort of like to have dx be at the end, it's really a multiplicative term here, so there's nothing wrong at all with that dx sitting right there for the moment. I typically stop, though, and rewrite these things like I actually more typically used to seeing, x to the 1/4 dx, right? So now we've built the integral of interest, so let's go ahead and do the integration here. I'm going to add 1 to the power, adding 1 to, since this is x to some power, I am going to use the power rule. I add 1 to the power, that's going to give me x to the 5/4. But I noticed that if I were to take the derivative, it would pop down a 5/4 in front. I don't want 5/4 of x to the 1/4. I want one of them. And so I'm going to introduce a coefficient that will perfectly cancel that, a 4/5. Now, if I take the derivative of this guy right here, you'll see the 4/5 cancel with the 5/4 that comes down, leaving us with one copy of x to the 1/4 right there. This is the guy that I would like to evaluate from x equals 0 to x equals 1. And once again, it looks like we get a pretty simple evaluation right here, especially because of the 0 part of this right here. And it looks like what we're getting here is 4/5 times, and we're getting 1 to the 5/4 minus 0 to the 5/4. Notice that the 4/5 is just a constant, so I'm leaving that out front when I do my upper bound minus my lower bound stuff right there. And it does look like where then it's that this is just all going to be 1 in here, right? 1 to the 5/4 is 1, 0 to anything is 0. So this is just 1 within the parentheses. So it looks like we're just going to be getting an answer here of 4/5. Now, as I'm doing this, I'm laughing that here we go. Here's Tony's first mistake of the semester. And so what I'm going to do is I'm going to tell you I just made a small mistake in this right here. If you would like to pause the video and figure out the mistake on your own, I would encourage you to do that. Otherwise, what I'm going to do is let's go ahead and do this other one over here. Let's see that we're going to get a different answer, and we're going to say, oh no. And then we'll come back and we'll find the mistake that I just made. I made a little tiny mistake in this guy right here. So let's go ahead and do our second one right here and have the oh no moment. I didn't get the same answers. And we'll come back and find our little small mistake that I made here. So doing our dy version on this guy, I now have a horizontal Riemann stick. This Riemann stick has a height now. That's our delta y for our Riemann stick, or our dy when there's an infinite number of Riemann sticks. And now the thing here is that this needs to be, it's a width x, but I'm going to want to describe that width x in terms of y. So it looks like one of the things that I'm going to have to do here is sort of flip this equation around, right? It looks like we have that y is x to the 1/4. Well, I can take the 4th power on both sides and get that y to the 4th is what x is going to be. So it looks like we're going to want to be using this y to the 4th power as our representation of what x is. X is y to the 4th in this scenario here, right? That's what our curve is exactly describing. And so here I'll say x, where x is y to the 4th. So again, I'm going to set up my same statement here. Area is the integral of x stuff times y stuff. In this case here, it looks like, what's my y component, the heights component? That is just our dy, right? So I can go ahead and put dy in for our y component. What is the x component? What's the width of each of our Riemann sticks? The width of each of our Riemann sticks is x. But I want my x to be described in terms of y, since that's the variable of interest for our integrand right here. So for my x stuff, what is x? It's y to the 4th. Now that I know that I'm doing a dy integral, I know that what I'm doing is I'm taking this horizontal Riemann stick here, and I would like to add up the area of each of the horizontal Riemann sticks for the full span of the y values that are of interest here. Well, it does look like in this case our y span matches our x span. It looks like the y values also go from 0 to 1. So it does look like we're going to get the same bounds of integration here. But notice real importantly for a quick second that this 0 and 1, those are y values. This 0 and 1, those are x values. It's a coincidence that they're the same in this problem. It's not necessarily the case that those should always match right there. All right, these are y values, these are x values. So let's go ahead and do this, see that we're going to get our different answer, and we'll go back and fix the first one real quick here. This integral looks like it's going to be pretty easy for ourselves right here. I'll do our rewriting without all the parentheses clogging up our view right here as well. I'm going to add 1 to the power. That's going to give me y to the 5th. But I know that if I were to take the derivative, that would give me 5y to the 4th. And I only want 1y to the 4th. So I'm only going to keep 1/5 of what I'll get out of this derivative right there, so that 5 and 1/5 cancel, leaving us with y to the 4th. I can go ahead and evaluate this guy from y equals 0 to y equals 1. And it looks like I'm, again, going to get a nice and easy evaluation right here. It looks like this is 1/5 times 1 to the 5th minus 0 to the 5th. And it looks like this is just going to be 1/5. So now my question is, where did I go wrong in my previous one right here? So I want to show you graphically why this guy here was a slightly nicer setup on the right than what we had on the left here. The thing that's nice about this setup that we had right here was that our measurements started on an axis, right? When I see this Riemann stick right here, we started at 0 and measured out to the end of its width. But we didn't do that here. What I think I did wrong right here is this. When I said, what is the height of each Riemann stick, I wanted to know the y value. How tall was this stick right here? And what I incorrectly said was that the length of this stick, remember, I'm trying to measure the length of this stick. I claimed that the length of the stick was what our y value was at that location, but that's not quite right. Notice that the y value is the height from the x-axis up to the curve. I wanted from the curve up to the line y equals 1. It's not the same chunk, right? So I'm going to say that again. Really, if you're looking at the y value of any point on the line, on the curve, excuse me, what that's describing to you is the height from the x-axis up to the curve. That's the y value, and I used y incorrectly. What I wanted instead was from the curve up to the line y equals 1. That's a different quantity there, right? So what I'm noticing here is that our value of interest is really, if you start with the entire length from 0 to 1, which is 1, I really want to subtract off our associated y value that we have right there. Right? So it looks like the actual height of this stick is 1 minus the height that's underneath our curve, which is y. So it looks like rather than doing our y stuff as just y, what I really wanted this to be was 1 minus y in there. And that will give me the actual height of our Riemann stick. Again, I'm going to take the entire height from 0 to 1. I'm going to chop off the bottom chunk of the height, y. So that's 1 minus y. And that will give me the remaining height, which is the height of my stick right here. So here's what I want to fix for myself now. Let me go ahead and I'm going to get rid of this. And then I guess I should get rid of all these guys down here. And we'll go ahead and fix this guy and see if this is going to match up then. All right, so again, what I'm going to do is rather than using y, I am using 1 minus y. And the reason is because our measurement wasn't starting from an axis, right? The bottom of the rectangle, at no point is this rectangle touching like the x or y axis, except for the one infinitely thin rectangle that's right here in the corner, right? So this height starts at y and goes up to 1 here. So it looks like my y stuff is really 1 minus y. All right. So again, the other thing I would like to encourage you guys to do here is don't feel uncomfortable about writing integrals like this. Even though I can't do this integral like this yet because I have y stuff and a dx integral, this is still getting me there, right? This is helping me see what was the component. The height of this thing really should have been 1 minus y, right? I'm going to just do this. That should be 1 minus y for the overall height that's right there. Now I can stop and say, and what was y? Oh, it's x to the 1/4. I can do that. So it now looks like what I'm really interested in here is 1 minus x to the 1/4 dx. X values are still going from 0 to 1. Now when I integrate, the integral of 1 will give me x. The integral of x to the 1/4 will give me, again, it's going to become 5/4. So I need the 4/5 out front, x to the 5/4. And we are evaluating this from x equals 0 to x equals 1. I can now go ahead and evaluate here. It looks like I'm going to get 1 minus 4/5 times 1 to the 5/4 minus, and we can see that we're going to get just a bunch of 0 that's out there. And so it looks like for our final answer, I'm getting 1 minus 5/4, or sorry, 1 minus 4/5. And that's going to give me the 1/5 that matches what we got on the other side right there. All right, so there we go. So I made my first little mistake, as you will do this semester as well. And again, I know I've said this like 4 times already. I'm going to say it a 5th time. The hard part here is building the integrals properly. Doing the integration, not that bad. You're going to do 1,000 integrals this semester. Building them smartly, that's the real challenge. That's the really important part to this right here. So recognizing that the height of this is not y, because the height y is what takes you from the axis to the curve. We wanted to go from the curve up to the line y equals 1. So we measured our heights of each of our rectangles slightly differently there. So this is maybe one thing to say to you, that if you are ever considering for yourself, do I want to do vertical or horizontal Riemann sticks? Sometimes one of the reasons I will pick one over the other is to say, well, I don't know, does the Riemann stick touch an axis, meaning that my measurement is a little bit easier, or are all my Riemann sticks sort of floating out in space where I have to think a little bit more carefully about what their components are, their lengths and their widths actually are right there. Right? So both of these had their own little snags. Again, notice in this one we had to rewrite our equation in terms of the other variable here. We had to go from y equals x to the 1/4 to x equals y to the 4th. But I think that's an easier flip right there than doing this guy. But again, you should definitely be able to do this both ways. So good. Real quick, we want to talk about a units problem right here. This 47 is not doing any real math right here, but this is a reminder of a very important units lesson that's associated with thinking in terms of integrals. This question heavily relates to the fact that I write often my integrals thinking, well, it's just length stuff times width stuff, right? Remember that this really is a multiplication that's happening in here, and that this dy isn't just telling you the variable that we're integrating over. It's really one of the multiplicative components. It's one of the measures of the Riemann object that we're accumulating here. So in this question, I'm saying oil leaks from a tank at a rate. Oh, that's such an important word right there. Rate. Hopefully Calc 1 burned into your brain that rates are mathematical quantities here that are related to calculus, of r of t gallons per minute at time t. Then what does the quantity, the integral from 0 to 120, r of t dt, represent? And the easy thing that I'm going to do right here is I'm just going to write some units. All right, when I think of r of t is gallons per minute. This is gallons per minute. That's r of t. I am multiplying r of t by dt. And again, I'm going to say to you, that dt, that dx, that dy on the end of all your integrals, those aren't just indicating the variable over which we're integrating. That is a term that's multiplying some quantities within the integrand here. This dt, it's an infinitely small change in time, right? So this is some measurement of minutes right here. It's a time measurement, right? So that's got units of minutes right there. Well, what do you know? When we multiply together lots and lots of gallons per minute times minutes, what are we going to end up getting? It's a total measure of gallons. So this is just your reminder that unit math is a very, very smart thing for you to do. I feel like this is something that physics students usually have already been trained to do, but people who aren't necessarily physics people tend to think in units slightly less in my experience. I would encourage you to think in units kind of all the time now. Since calculus is about rates of change, that's always going to be like a fractional unit like this, and it's always valuable for us to do our unit math. So this should be the total gallons leaked over the first 2 hours. All right, 120 minutes, 2 hours right there. So the important part here is we can do the unit math to find that the quantity that we're getting out from this integral will be representative of a number of gallons. We know that the time span went from 0 minutes to 120 minutes right there. All right, so never forget that there's units that are worth considering in all the calculus that we do here. All right. So let's get back to actually building some integrals here. What we're going to look at here in problem 54, just real quick and remind myself, okay, we got two more here. We're going to talk displacement, we're going to talk distance, and we're going to talk position, velocity, acceleration. Those are kind of the things that the textbook laid out in their 8 examples for the net change theorem. We're going to kind of look at 3 of those 8 things in these next 2 examples here. So we're going to use this velocity function to find the displacement and the distance traveled over the time interval 1 to 6. All right, so real quick, let's talk conceptually about the difference between displacement and distance. Because these two things are very, very easy for us to overall confuse here. All right. When we're talking about displacement, what I really want to know is how far away am I at the end than I was at the beginning? So an important example to think about is if I go to the grocery store and then come home, my total displacement is 0 because from start to finish, there is no difference in my location, right? I start at home, I end at home. But if I live 2.5 miles from the grocery store, then the distance traveled will be 5. The reason that we see 0 for displacement and 5 for distance is because the 0 comes from doing a positive 2.5 miles followed by a negative 2.5 miles. When those are added together, we get 0 miles of displacement. However, when we are looking at the distance traveled, I don't care if those miles were in one direction versus the other, left versus right, east versus west, going to the store versus coming back from the store. I want to just add them all up as positive distances rather than allowing there to be any form of cancellation. So when we're computing our distance, I'm going to want to make sure to take absolute values, right? I want to say, I don't care that the 2.5 miles going to the store was making me further from home and the 2.5 miles coming home was making me less far from home, a positive and a negative. I just want to get 2.5 plus 2.5. So we want to absolute value each of our chunks of our travel. And how do we know how to break up those chunks? Well, I'm not quite sure. Maybe we should draw a picture first here. Right, so we've been given a velocity function. Again, we want to find displacement and distance. Think of the grocery store example as to how do you distinguish between displacement and distance in your head there. Again, remembering displacement is how far are you from where you started when you're at the end. If you went to the grocery store and came home, the answer is 0. But the distance that you traveled would be twice the distance from your home to the grocery store because you went there and you went back. So let's go ahead and draw a picture here to kind of like fill in the rest of the information that we need here, and we'll go ahead and do both the computations. So we're interested in this velocity function right here. I guess I kind of want to graph this guy so I can kind of see some points of interest on the graph. One thing I'm thinking to myself right now is that it's quadratic, so I do feel like the first thing I should do is this factorable? Yes, it looks like I can do a t minus 4 and a, well, it's not an x, and a t plus 2. I think that'll give me the minus 8 on the end. That'll give me the minus 2 in the middle right there. So it looks like we're going to be dealing with, and I know that my times go from 1 to 6, so I know I'm mostly good with at least the right-hand side of my graph here. I should be experiencing, oh, that's not necessarily true. I do need to go to the left a little bit here. All right, so here we are at negative 2. That's one of my roots. Here we are at positive 4. That's another one of my roots. And I guess I should go out to 5, 6, since that's my time of interest right there. This is my velocity. So it looks like we've got an opening up parabola with roots at negative 2 and at 4. Uh-oh, I got to draw a parabola now. Can I do this? I don't think I can do this. I set myself up to draw a pretty big parabola here. Oh, I got to keep going too. Oh my gosh, okay. Good enough. Man, it's hard to draw big shapes with this pen. So what we know that we are interested in is we are interested in time 1 to time 6, right? So I'm going to go ahead and kind of mark off those bounds. We're really interested in this region right here. This is our time 1 to time 6, right? There's some edge point that's up there, right? Maybe I'll get a little bit of... All right, this is our region of interest. This is t equals 1 to t equals 6. All right. The thing that I'm noticing here is this. It looks like our velocity is negative for the first chunk of our trip from time 1 to time 4. Then at time 4, our velocity is at 0. And for all times between time 4 and time 6, we have positive velocity. So this seems a lot to me like our going to the grocery store example. It seems like for a while we moved in one direction, and then we turned around and we went the other direction. Right? So it looks like we are going to have that distinction between distance and displacement in this case here. So I think the easier one to do is our displacement first, because the displacement is just the overall change in position that we're going to end up experiencing, right? So some small things real quick here. One, remember that when we're integrating a velocity function over time, that this is like meters per second times seconds, and that this is giving us meters. This is distance right here, right? So notice one thing here is that the integral of a velocity function is always going to give you a position amount, or position function if it's indefinite, a position amount if it's definite for our integral here. We have a definite integral since we know our bounds, right? So the total distance traveled, or excuse me, the total displacement here. All right, here's what I should do. I shouldn't write distance there since we're talking about the distinction between distance and displacement. I'm going to write position right here as a sort of a neutral word that's more talking about location instead of velocity, but not conflating it with our two kind of vocab words right here. So our displacement is the easier of the two, I think. Displacement is just going to be the integral from 1 to 6 of our velocity function. It's just the total. How far are you at the end from where you started? How far are you away at time 6 than you were at time 1? We know that we're doing a little back and forth in here. We're going, you can think of this as going to the left for a while and then going to the right for a while. It might be that we landed back on the same exact location because we had some negative velocity and then some positive velocity. Based on the way that I drew this graph, it looks like the negative area is a little bit more than the positive area, but I also drew a really crappy graph here, so I don't want to go judging my parabola. Let's just go ahead and do the calculus here. So I've got my velocity function here. This should be integral from 1 to 6 of t squared minus 2t minus 8 dt. I will do the integration here. I'm going to get a 1/3 t cubed. I'm going to get a minus t squared and minus 8t, right? Stop for a moment, take the derivative of what I just wrote, convince yourself that it is in fact the integrand on the line above it right there. I do a lot of integration by guess and check. I do a lot of just flopping some things out there and then taking the derivative and saying, did I get that right? Okay, I'm good. Guess and check is a good technique here, and you certainly should be using it for integration, things like this. We are doing this. Oh, so unfortunate. We don't have t equals 0 for our lower bound. We actually have to do a little bit of math here, but t equals 1 is our second best, our second easiest thing that we could have here. So what are we going to end up getting here? Oh man, we got big numbers and everything. 1/3 times 6 cubed minus 6 squared minus 8 times 6. Subtracting, and by the way, I'll take a moment to say it right now. We know that we're doing like our capital F of B minus our capital F of A. You gotta use your parentheses right here. So many times people don't use these parentheses and then only subtract off just the first term of what comes next. Make sure you get the parentheses and distribute that thing here. I'm gonna do a little bit of shorthand here. Notice that when I plug in t equals 1, all of the polynomial terms survive. We basically just get their coefficients, right? So this should be 1/3 minus 1 minus 8 in there. And now I just got to do a little bit of computation. I might need a little bit of calculator help right here. No, I don't. 6 cubed divided by 3, that should really be like 6 squared times 2, which is 72, minus 36, minus 48. Seeing if I still remember how to do mental math after taking a break for a month. And then over here, it looks like we've got negative 9 and a positive 1/3. So I'm thinking of this as negative 27 thirds, and that makes it negative 26 thirds. And now I just got to add this stuff up right here. So what did we get? We got 72 minus 36 minus 48. That's going to give me negative 12. So here I'm getting negative 12 plus 26 thirds. And so I can think of negative 12 as 36 thirds. So negative 10 thirds, or I could maybe say negative 3.33 miles of displacement or units of displacement right here. But it looks like that's what I'm finding for our total total displacement for this guy. Did I get my fraction right here? I think I did, yeah. All right, so there's our displacement computation right here. It's the easier of the two. It just says accumulate all your change. Now, distance is different, right? What we need to acknowledge now for distance is that we were traveling to, and I'll think of this as to the left for a while, channel, but I want to accumulate that as positive area now. And we were traveling to the right for a while. This will naturally get accumulated as positive area, but maybe I didn't know which one was positive, negative. It's typical to just put all these things in absolute values for each of our chunks right here. Notice that one of the very, very important parts of this one is that we have to know where this location is. This t equals 4 seems to be sort of our breakdown, right? It seems like from 1 to 4, we were going to the left, and then from 4 to 6, we were moving to the right. We would like to accumulate the positive distance traveled over each of those subintervals right there, right? So what we're doing is we're sort of decomposing our full interval from 1 to 6 over chunks of consistent direction, right? This was all to the left, this was all to the right. If there was another change in sign, we'd have to do a third chunk for this guy right here, right? So it looks like our distance traveled is going to be our integral from 1 to 4. All right, I need to throw my absolute value bars out there. From 1 to 4, this is our going to the left parts right here, v of t dt, plus some more distance that we got. Now, we know that the second chunk is naturally positive, but I'm sort of being formal with my absolute values. Can I not write a 6? What's going on here? All right, 6, and again, our v of t dt. So again, notice that one of the big keys for our distance traveled is we needed to be able to do the algebra to know when did we experience that change in direction right there. I'm going to draw one other picture I think will help with this guy a little bit here in a minute. In any event, we've actually already done the integral, right? We just need to deal with our bounds of integration a little bit differently right here. And so let's see here. It looks like we should be getting, maybe I can do this for myself right here. I'm gonna do myself a little favor relative to what we've already done. I'm gonna say capital F here, our antiderivative, our integral of v of t dt is our capital F of t. And we already did this. It's this expression right here, right? It's this 1/3 t cubed minus t squared minus 8t, right? This is what I want to be evaluating. This is my bounds of integration, or sorry, my results from integration. I need to apply my appropriate bounds of integration to this antiderivative right here, right? So I'm just trying to reuse my work because I've already done this integral, right? I know that I'm taking the integral of v of t. I just need to alter what my bounds are that I'm dealing with right here. And so I'm going to write this now as, what do we got here? We should have the absolute value of this 1/3 t cubed minus t squared minus 8t evaluated from t equals 1 to t equals 4. We're taking the absolute value of that whole expression. And by the way, I know this is going to be negative, right? And I can see that we're accumulating that because we're moving to the left. We should have a negative position at the end of this. On the other hand, our second quantity over here, I am going to keep this in our absolute values, even though I kind of know that that's not really a thing for this guy right here, 1/3 t cubed minus t squared minus 8t. And we're evaluating this guy from t equals 4 to t equals 6, and the whole dang thing wrapped up in those absolute value bars here. So let's go ahead and do our evaluation and find our distance traveled. I'll draw one last little picture as well to kind of make sure that we see exactly what happened here, and then we'll move on to our last problem here. So here it looks like I'm going to be getting for myself absolute value of, I should be getting 1/3 times 4 cubed minus, and I'll do a little bit of, try to quicken up my math a little bit here. That's our first one. Our second one here, we're going to get our, and gosh, I'm going to steal some more stuff over here, right? I've already done evaluating this guy at 6. When I evaluated it at 6, I got -12. So that's my evaluating at 6 minus evaluating this guy at 4. And when I evaluate this guy at 4, I will again get 1/3 4 cubed minus 16 minus 32. And now I just got to evaluate here. So let's see here. 4 cubed is 64, so I'm going to get a 64 thirds minus 48 minus, and this was again our This gave me the negative 26 thirds inside the parenthesis. The negative makes it a positive 26 thirds. And I'm expecting this overall to be negative within here, but then when I take the absolute value for it to become positive, and we can see what 64 plus 26 divided by 3 is going to be giving me 30 minus 48 will be giving me absolute value of negative 18. So what this really says to me is in the first, from time 1 to time 4, it looks like we went 18 units in the negative direction. But since we're looking at total distance, I just want this to say we went 18 units. That's why we're doing the absolute value there. The second chunk of this guy over here, it looks like I'm going to be getting negative 12. And again, we've already done this one. No, wait, we haven't done that one. This, well, I guess we have. We just did it over here. So this should be our 64 thirds minus 48. And I'm going to do my 64 thirds minus 48. That's going to give me negative 80 thirds, but we're adding that to the 12. All right, this is a negative quantity inside the parentheses there. I'm subtracting a negative to get the positive right there. And so 80 thirds, 80 minus 36 is going to be giving us 44 thirds. And as expected, this is the absolute value of 44 thirds. It was positive like we knew it would be. And so it remains positive because it was in the absolute value right there. So it looks like we are getting in total, if I want to give this just a decimal answer right here, looks like I'm seeing a 32.67. That's right. Or 98 thirds. I'm getting for my total displacement right there. So really kind of what I'm seeing here is when we started at time 1, we were moving to the left. At time 4 is when we turned around, and then until time 6, we went to the right. In total, we actually ended up to the left of where we started from. So it looks like our kind of diagram for this guy is we started here at time 1. We went to the left for a while. At time 4, we turned around. And then we kind of went back and we landed still a little bit to the left where we started. Right? This was sort of our progression right here. Right? So we still ended to the left of where we started. That's the negative 10 thirds units of displacement from where we started. But the entire trip, the length of this little curve right there is going to be the 32.67 units that we've got right there. So I sort of like to think in terms of these sort of like one-dimensional, two-dimensional graphs right here. This is sort of like half one-dimensional and half two-dimensional. Since we're only describing one variable, it shouldn't really have like a difference in vertical height right there at all. That's just for me to help kind of visualize it for myself right there. But I kind of like the idea of this diagram right here to kind of visualize what we're doing. So keeping track of the distinction between displacement and distance traveled is important. And again, recognize that one of the key things of this is that I couldn't have computed my distance traveled if I wasn't able to algebraically determine where we had our turning around point, where we changed directions. That ended up being where we broke down our integrals at. And again, it might be that there's more than one of these. It might be that you're changing directions all the time and you need to add up lots of absolute value integrals to get your total distance. Displacement is always easy. It's just the integral from the beginning to the end. So displacement is the easy natural one. Distance traveled, you got to stop and find out where we cross the x-axis to find your breakdown locations there. So let's go on to our last guy here. Do a little bit more of a physics problem here. If you're not a physics student, don't worry. Calculus was invented to do physics. So by virtue of being a math student, you are a physics student. Every math student is expected to learn a little bit of physics because like calculus was invented to do physics. It's at least, at the very, very least, it is the historical part of this calculus class here. So a particle has some given acceleration, and we know what velocity the particle starts with. What we would like to find is the distance traveled over the time interval from 0 to 3. Right? So what we've been given is a little bit of acceleration information, a little bit of velocity information, and what we want is distance information. So remember sort of the hierarchy of this from Calc 1. We start with position. The rate of change of position is velocity. The rate of change of velocity is acceleration. So what that means to me is, since I just described two derivatives to get from position to acceleration, if I want to get from acceleration to position, I got to do two integrals, right? It's just going back in the other direction out there. So just kind of notice real quick that when we do the integral of acceleration with respect to time, that is going to be, this is meters per second squared times seconds. So that's going to cancel with the squared, and that leaves us with meters per second, which is velocity. Then we do our integral of velocity with respect to time. That's just meters per second times seconds for the dt. Those cancel and leave us just with meters, which is position, right? So we know that there's sort of like a two-tiered relationship between position and acceleration. Velocity is what's in between them. Depending on which direction you're going, you either need to use derivatives or integrals to get there. Okay? So it looks like something I could do is I could take the integral of our acceleration term, and that would give me velocity. I could then take the integral of our velocity expression that we got out, and that should be giving me our final position right there, which is really what I'm interested in. So let's go ahead and do that. Notice that we're also going to need to use this one extra little piece of information right there. So that was sort of our concept right here. Now let's actually do it. So our integral of acceleration. And again, I'm just trying to find a velocity function right now. I'm not trying to actually accumulate any distance, because the integral of acceleration doesn't give me distance. It gives me velocity. So notice here, very importantly, I don't have any bounds of integration here because I'm not trying to accumulate acceleration. I'm only trying to come up with a function for acceleration that I can then integrate a second time. For us here, this integral of acceleration then is going to be 2t plus 3 dt. Not too bad to do. This should just be giving me t squared plus 3t. And now I'm going to give you your first set of crazy eyes for the first time this semester. What goes on the end? You better not forget it. A plus c always, right? There could have been a plus c out there. Think back to if we were to take the derivative, right? If you take the derivative of this, you are getting back exactly this integrand. There could have been some plus c on the end that we just were unaware of. We have to include it for this sort of, in a sense, a possibility of that. This is our constant of integration right here. It's really important. Don't forget your constant of integration whenever you're doing your indefinite integrals as opposed to our definite integrals when we have bounds of integration. So it seems like this is a generic velocity function, but sort of my problem is I don't want to see in my velocity function. Well, great news for us. We can now go ahead and apply our initial condition here to help figure out what value c must be taking on. So we know that v of t is t squared plus 3t plus c. I'm going to go ahead and apply the initial condition. V of 0 equals negative 4, and therefore V of 0 equals negative 4 equals 0 squared plus 3 times 0 plus c, and that's going to tell me therefore that c must be negative 4. And now I actually have a full expression for velocity. So it looks like I now know this is really t squared plus 3t minus 4. The important thing is I now actually know a legitimate velocity equation without any constants of integration in there. This is now the equation that I can use to now accumulate changes in velocity to get to position. If I could ever, come on, end button, there we go. So now we can go ahead and integrate our velocity expression, but this time using bounds of integration, because now I actually want to say, okay, accumulate these changes in position over time to get an overall change in position. Find the distance traveled. So this is just going to be, oh wait, do I need to, oh, never mind, this is our distance traveled. So now I got to stop and think about my velocity expression right here. So it looks like our v of t, I can go ahead and write this guy as, what, t plus 4, t minus 1. It looks like that's my factored form for this guy right here, which says to me this looks like a parabola with roots at time 1 and at time -4. We are interested in time from 0 to 3. So it does, again, look like for distance traveled, we're going to need to go ahead and go from 0 to 1 as our first chunk, and then from 1 to 3 as our second chunk, take absolute values of each of those individual parts. It wasn't asking for the displacement. It was asking for the total distance traveled. So, and by the way, maybe I should point out one thing real quick. Notice that we're starting at a negative velocity, but that our accelerations are always going to be positive because acceleration is 2t plus 3 and our times are positive right here. So we started with negative velocity, but we're always increasing positively that velocity based on acceleration. So it does make sense that we went from going to the left to later going to the right based on our acceleration that we can see right here. So it looks like we should be getting then for our sort of our answer then is our distance should be our absolute value of the integral from 0 to 1 of our velocity function v of t dt plus the absolute value of the integral from 1 to 3 of v of t. I know that I was going to the left here, and I know I'm going to the right here, but I just want to accumulate the distances traveled, not keeping track of the lefts and the rights here. This integral looks like it's going to be pretty nice to evaluate because it's got bounds of 0 and 1. Also, I'm noticing we don't have any crappy fractions to deal with out here, so this looks like it'll be a little bit nicer than the last one. So, what are we getting here? This should be our integral from 0 to 1 of t squared plus 3t minus 4 dt, and similarly here. All right, let's do the integration, call it a day here. I am seeing here, oh no, we are going to get the fractions, sorry. I was thinking that we were only doing the one step of integration. We got more integration to do. We're going to get kind of very similar fractions as we got in the last problem here. So what I'm seeing here is we're going to be getting a 1/3 t cubed plus 3/2 t squared minus 4t evaluated from t equals 0 to t equals 1. We're taking the absolute value of all that. Similarly here, same thing. 1/3 t cubed plus 3/2 t squared minus 4t. We're evaluating this guy from t equals 1 to t equals 3. This is one of the less easy because these bounds of 0 and 1 are really nice. When we plug in 0, the whole thing goes to 0. When we plug in 1, we just keep the coefficients. So this is just going to end up being 1/3 plus 3/2 minus 4. That's one chunk. Minus 0 for the second chunk right there. Notice this is giving us a negative number right here. We were going to the left. We're going to take the absolute value and get a positive, but we see that this did indicate position to the left right there, which is in agreement with what we knew was happening here. Second one, this one's going to be slightly more annoying right here. It looks like we're going to get 1/3 of times 3 cubed plus 3/2 times 3 squared minus 4 times 3 minus, at least the 1 is nice to us again, 1/3 plus 3/2 minus 4. So what is this in terms of fraction? I guess I'm thinking of this in terms of sixths. So what do we get right here? We got 2/6 plus times 3 is going to be 9/6 minus 24/6. So that's 11 of them. Take away 24, we get negative 13/6 for a total of positive 13/6 once we take the absolute value right there. And on our other guy over here, a little bit grosser, 3 cubed divided by 3 is just 3 squared. So that's going to be 9 plus, 27/2 minus 12 minus, and this will be another instance of our, it's the exact same thing as that guy right there, right? So we're going to get negative 13/6 from this guy. And now we can go ahead and wrap this up. It should be plus the absolute value of 9 minus 12 is negative 3. And so maybe I'll write that as a negative 6/2 plus 27/2 plus 13/6. what do we got here? That's going to be 21 halves, but I really want to think about that as like 63 sixths plus 13 sixths is going to give me 76 sixths. 89 sixths is what I'm getting for our total displacement on that guy, and that should not reduce at all. Not reduce at all. So, given that I handled all my fractions correctly, which I always get a little nervous about when I'm wrapping up a problem right here, conceptually speaking, are very important things right here where we were given our acceleration information. We integrated acceleration to get velocity. We needed to know an initial condition for velocity, or else we were gonna be stuck with that constant of integration. Since we had the initial condition, we were able to get a full velocity equation. And integrating velocity over a time interval will give you our distance traveled. Excuse me. That will give us our displacement, but we broke it down over the moving left parts and the moving right parts to get our total distance traveled, separating these up with our absolute values right here. So this one kind of encompassed both ideas, our position, velocity, acceleration relationship, as well as remembering that distance traveled is taking the absolute value of each of the directions of motion that we've done. We did some stuff to the left, we did some stuff to the right, but we just really want to accumulate the total amount of travel experienced. Not accounting for the leftness and the rightness of this thing. So here I am at 1 hour and 16 minutes, which I got to say, in a regular in-person class setting, we would have hour and 15-minute long classes. I know that some of you that are taking this class right now have had me in the past, in which case I'm pretty sure I've gone over by at least 1 minute every lecture I've ever done in person in my entire life. So as far as I'm concerned, I just nailed it right here. In general, I am going to try and, for everybody's sake, keep these videos like as short as I can, but I just can't shut up a lot of the time, so sometimes these drag out a little bit, but I'm going to do my best to be consciously aware of that this semester and not just make videos be frivolously long without good content in them for you. So these are the examples I wanted to walk through in section 5.4. So your big things are you've done your 5, 1, 2, and 3, so you're refreshed on Riemann sums and integrals. We need to remember things like the integral relationships between position, velocity, and acceleration. We want to remember our distinction between distance and displacement. And we want to remember units are your friend. They can help make things that seem difficult be very easy. They can help validate the stuff that you're doing. We did our integral math, or sorry, our unit math right here, also to kind of convince ourselves about the acceleration, velocity, position relationships. And finally, I think one of our biggest things that's going to follow us for the next few weeks is thinking in terms of Riemann objects. I would strongly encourage you to be drawing these pictures whenever you are attempting to come up with the area associated with any region, because we're going to be dealing with volumes right away in a few weeks here, and we're going to use the exact same concept. So thinking in terms of Riemann objects, drawing your Riemann sticks, literally writing out the dimensions of each Riemann stick as your integrand, I think are some really valuable concept things to do. That I do really like our book, but I want to see a book that like clubs you over the head with Riemann conceptualization, and so I'm going to do that since I've never found a textbook that does. So that wraps up our 5.4 content here. 5.5, our next section, covers U substitution. By the way, you can see that right above my head right there. It's called the substitution rule. There's literally nobody that calls it that. It is generally referred to as U sub by any mathematician or physicist or any person that does calculus. It's sort of one of our most important basic rules of integration, right? As of right now, all we can do is like integrate using the power rule or things where we already know the antiderivative. U sub is essentially going to undo the chain rule for us. And since the chain rule is like the most important derivative rule, U sub therefore is conversely arguably the most important integration rule because it undoes the most important derivative rule. So that's what we'll get for U sub next video. I will see you guys then. Have a good one.